It's a real pleasure to be here, and I'm particularly happy to be able to give this talk in this year of 2015, because this year we're celebrating the centenary of Einstein's theory of gravity, general relativity, or GR for short. So 100 years ago, not quite yet, but in November, Einstein was putting the finishing touches, the final details together about his theory of gravity. And I want to talk to you about general relativity and tell you about it with a slightly different emphasis, perhaps, to the way that it's often presented. So general relativity, as all major advances in science, did two things. The first thing that it did was it brought into science something which had previously been considered outside of science, something that had been previously considered fixed and unchanging, some kind of background on which science takes place. And general relativity brought that thing into science and breathed physical, dynamical life into it. And that something is space-time. And I'm going to talk much more about space-time during this lecture. The second thing that general relativity did was it opened the door to new arenas for science and new areas for physics. It posed new questions, new problems, and some of those problems are still as yet unresolved. The arena of physics that was opened up by general relativity was the physics of what we might call outer space. That is the physics of compact objects such as that are distant from us, such as neutron stars, pulsars, black holes, the physics of galaxies, and also the physics of the universe as a whole on the largest distances that we can observe. And general relativity has been extremely successful in explaining the physics of outer space. Many phenomena that we observe using our telescopes have been successfully explained and interpreted using general relativity. But something that's not really often emphasized is that general relativity also accords well with, is particularly in tune with, what I would call our inner space, or our intimate experiences. And that's what I want to draw out during this lecture. And I want to claim that general relativity accords with that inner space, with our intimate experiences, much better than the theory that general relativity replaced, which is Newton's theory of gravity. So that's my claim, and I'm going to try to convince you of that this afternoon, and I'm going to use two concepts to do that. The first concept is the concept of gravitational force, and the second concept is the concept of time. So that's my aim. I'm aiming to convince you that general relativity accords better with our inner experiences, our intimate experiences, than does Newtonian gravity. So I have to tell you about Newtonian gravity first, because I'm going to do a contrast between the two theories of gravity. So what is Newtonian gravity? Well, Newtonian gravity successfully explains and was developed and created to explain two facts. The first fact is that all things which fall freely from rest fall together if they're close enough. And this thought is often attributed to Galileo. And Galileo did not the real experiment, but had conceived of a thought experiment in which two objects of different masses, let's say a bowling ball and a marble, were dropped off the Leaning Tower of Pisa, dropped from rest, so they're not thrown down or up, but just held and then dropped together. those two objects, even though they have different masses, would fall exactly together and hit the ground at the same time. So that's Galileo's thought experiment. And indeed, it is an experimental fact. If you do such experiments with freely falling objects, then they do indeed fall together, no matter what they're made of and no matter how massive they are. The second fact was a whole collection of facts, actually, but that consisted of celestial mechanics. That is, that planets orbit the sun, the moon orbits the Earth, and here I've got a little Earth. Think of my hand as the sun. And the orbits are approximately circles, not quite. They're better described as ellipses, but nevertheless, they're very close to being circles. So the planets orbit the sun in very close to circular orbits. The moon orbits the Earth in very close to a circular orbit. So these facts were some of the facts that Newton put together that inspired Newton to come up with, to create his theory to explain these phenomena. And his explanation was very simple. His explanation was that there's a force, a gravitational force, that exists between any two objects in the universe. So, for example, the sun and the Earth. There's a gravitational force between them. There's a gravitational force that pulls on the Earth towards the sun, and the same strength of force pulls on the sun towards the Earth. And the reason that explains the planetary orbits, because just as this ball goes in a circle around my hand, because there's a force pulling on it, and that force is the tension in the string. So the reason that ball doesn't fly off in a straight line, but goes around my hand, is because it's being pulled on by the string. There's a tension in the string, a force on the ball, which keeps it going in a circle. And so Newtonian gravity explains the orbits of the planets in terms of this force, this gravitational force. The Earth orbits the sun because there is a gravitational force that's pulling on the Earth, keeping it in its orbit around the sun. So it explains the orbits, but it also explains Galileo's fact, the fact that falling objects, if they're close together, fall together. And it explains it because Newton's theory of gravity is a quantitative theory. It doesn't just say, oh, there's some force. It tells you how big that force is. And in particular, it tells you that the force, the gravitational force that's pulling the Earth, for example, towards the sun, is proportional to the mass of the Earth. And if you drop something down to the ground, it's being pulled down towards the center of the Earth by a force that's proportional to the mass of that object. So if I drop a bowling ball, then the force on that bowling ball pulling it down is proportional to the mass of the bowling ball. If I drop the marble, let's say it's 100 times less massive than the bowling ball, then the force on the marble is 100 times less than the force on the bowling ball. The force on the two objects is proportional to their masses. However, Newton's second law of motion says that the acceleration of an object is inversely proportional to the mass of an object. That means that if something is being pulled with the same force, if you have two objects which are being pulled by the same force, and one is twice as massive as the other one, then the object which is twice as massive will accelerate at half the rate. So the acceleration is inversely proportional to the mass. So the force on the larger object is bigger, because on the more massive object is bigger because it's more massive, but its acceleration is inversely proportional to that mass. So the two factors of the mass cancel out, and the acceleration of the two objects is identical to each other. So indeed, Newton's laws of motion and Newton's theory of universal gravitation explains the Galilean fact that falling objects, if you drop them, fall together at exactly the same rate, they accelerate at the same rate, and they will hit the ground at the same time. Newtonian gravity was extremely successful. It was used for decades and centuries to explain and predict the motions of the planets to extraordinary accuracy. However, it had a problem. And that problem goes by the name of action at a distance. So the Newtonian theory of gravity is that any two objects, for example, the Earth and some astronaut, are attracted to each other by this universal force, this force of gravity. And this force can be calculated quantitatively. It depends on the masses of the two objects, but it also depends on the distance between them. The further away those two objects are, the less powerful the force. The force is inversely proportional to the square of the distance between them. So if you double the distance between the two objects, the strength of the force goes down by a factor of 4. If you triple the distance between the two objects, the strength of the force goes down by a factor of 9. So it's inversely proportional to the square of the distance. And this force exerts itself through empty space. There's nothing in between the Earth and the astronaut, which are being attracted to each other. This force is just there. And this feature of Newton's theory was criticized by many thinkers at the time. And one of the thinkers who was around at the time of Newton said the following thing: that gravity should be innate, inherent, and essential to matter, so that one body, such as the Earth, may act upon another, such as the astronaut, at a distance through a vacuum without the mediation of anything else is, to me, so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. So that's a pretty trenchant criticism of Newton's theory of gravity. And the person who made that criticism was Newton. And it's interesting that Newton himself understood, so Newton was a consummate scientist, he understood there was something unexplained about this theory of gravitation, something that was something lacking, something unsatisfactory about this proposal that there should be this force that acts between two bodies and has no carrier, if you like. It acts at a distance between two objects which have nothing in between them. There's just a vacuum in between them. However, because Newtonian gravity was so successful in predicting the orbits of the planets, this more, what one might call philosophical worry, was just set aside, and people just got on with the business of doing science with the Newtonian theory. However, things came to a head in 1905. And they came to a head because Newtonian gravity is in contradiction with the new theory of special relativity that Einstein proposed as the way to understand electromagnetic phenomena. And if you know one thing about special relativity, then you'll know that special relativity tells us that nothing can move faster than light. So there's a universal speed limit in the universe, which is roughly 300,000 meters per second. And that speed limit cannot be 300,000 kilometers per second, sorry. That speed limit cannot be broken by anything, any physical influence. Nothing can signal to any other thing faster than light can propagate from that one thing to the other. However, in Newtonian gravity, the force between two objects changes instantaneously when one of the objects is moved. So think about the Earth and the astronaut. If, for some reason, the Earth moves slightly, suddenly, then instantaneously the distance between the Earth and the astronaut is changed, and the force on the astronaut will be different, and the astronaut will know that. So the astronaut will know that the Earth has moved. That's an instantaneous signal to the astronaut that the Earth has moved. And that's impossible in special relativity. Nothing can travel faster than light. No physical influence can travel faster than light. So this was now a scientific, physical contradiction between two theories, and that constituted a major crisis in physics. So no longer could people just sit around and think, well, there's something odd about Newtonian gravity, but it works so very well that we can just brush it under the carpet. Now there was a genuine crisis, a genuine contradiction between two different physical theories. But this crisis took 10 years to resolve between 1905 and 1915. The resolution was general relativity. So the resolution of this crisis was the creation of the theory of general relativity. And the first step is something that we all have evidence for from our own intimate experience. So we can take the first step that Einstein took in working out general relativity, and we can take it now. We can all have the experience that constitutes taking that first step, and you can have the experience sitting from the comfort of your own chair, and I invite you all to have that experience right now. I found that it helps if, in having this experience, people precede it by a few moments of mindfulness meditation. So I'm now going to invite you to meditate for a couple of minutes. You don't have to do it if you don't want to, but people have told me that it really does help to enhance the experience. So you don't have to do it, and it's perfectly fine if you just sit and don't participate in the meditation. But people have said that it really does help to have the experience. So if you like, I invite you to close your eyes. And the purpose of the meditation is to try to free the mind from thoughts and analysis and any kind of judgment. The idea is to experience something just by being aware of it without labeling it or analyzing it or giving it any kind of name. And it's often useful to focus your attention, first of all, on your breathing. So I invite you to breathe in, take a breath in, and breathe out a few times. And each breath in is a new beginning, and each breath out is a letting go. And if you can focus your attention on your diaphragm, where you can feel your diaphragm rising and falling as you breathe in and out. And if you feel your mind wandering, then don't worry, just breathe in and out again and refocus your attention on your diaphragm, rising and lowering. And now, as if there's a spotlight there on your diaphragm, move that spotlight downwards and focus your attention on your bottom. And just become aware of your bottom and the sensations there, in that location. Try to just become aware, be aware of the sensations in and on your bottom. And now bring the focus of your attention back to your diaphragm. Breathe in once, breathe out, and open your eyes. Now I'm going to ask for people to put up their hands and tell me what you felt when you were focusing your attention on your bottom. So I wanted you to just be aware of that sensation, but now I'd like you to try and name the sensation. Describe it in words. Would anyone like to? Pressure, good. I'm hearing a consensus of pressure. I'm sorry, say that again? Compression. So certainly the word pressure and compression, those words are used to describe forces. Would anyone like to say weight? Would anyone like to say what direction that pressure was in? So that I think I'm again hearing a consensus here that the pressure was upwards. There's a general nodding. I think that was definitely the consensus. Now that's very interesting. According to Newton's theory of gravity, there are two forces on you as you sit in your chair. There is the gravitational force of weight pulling you down. And to counterbalance that, there is indeed a pressure from your chair pushing you up. That's Newton's theory of gravity. That's how Newton's theory of gravity would analyze the forces on you sitting in your chair right now. However, I claim that if you free your mind from analysis and learnt theories, the only force that you can actually feel is the force of pressure pushing you up. And you do not feel any force pulling you down. And indeed, in general, even though the Newtonian theory says that force is there. And indeed, in general relativity, there is no gravitational force of weight acting down on you. It does not exist. There is no gravitational force of weight pulling you down. There is only a force pushing you up from your chair. It's the force that your chair exerts on you, pushing you up. This realization is what Einstein called the happiest thought of his life, and it was the first step. It was the first step that he took towards general relativity. There's no force between the Earth and an astronaut. There's no force between the sun and the Earth. So that explains, of course, the Galilean fact. When you drop two objects, let them go from rest, those two objects, there's no force on them. There's nothing pulling them down, no force on them at all. They move completely freely in a force-free way. And because they're moving completely freely, of course, they stay together because there's no force on them. They just stay together. They move together because there's no force on them. But how can we understand the motion of the orbits of the planets? So Newton's theory accords with our experience of whirling something around on a string because it says, well, something goes in a circle because there's a force on it, a force towards the center. Einstein's theory says there's no force of gravity. So how do we understand planetary orbits? Newton could not have understood that because Newton did not have what we now have, what physicists in the early 20th century had, due to the work of Faraday and Maxwell, and it's particularly pleasing to mention Maxwell here in this particular place to which he is so closely associated. Faraday and Maxwell had introduced to physics a new notion, the electromagnetic field. The electromagnetic field is a material substance that pervades space and time. It's everywhere, this electromagnetic field. They used it to explain electromagnetic phenomena. Einstein knew that he had to come up with, he had to postulate something analogous to that for gravity, a gravitational field that is everywhere. And the extraordinary thing was that this gravitational field is, it turns out, space-time itself. So the electromagnetic field of Faraday and Maxwell lives in space-time. The gravitational field of Einstein is space-time. And it turns out that to explain phenomena such as the orbits, this geometry of space-time has to be curved. Massive objects, such as the sun and the earth, create warpage in space-time itself. And other objects which are moving freely in space-time will move in that curved space-time as if they are being attracted to these massive objects by a force. There is no force there. They are just responding to this curvature of space-time. So the moon is moving freely in a curved space-time around the Earth, and it looks as if it's being attracted by a force, but in fact it's not. It's just responding to the curvature of space-time. Now, I claimed that there were two concepts which would bolster my argument that general relativity accords better with our experience than Newtonian gravity. The first was gravitational force. The second concept, which is absent in general relativity, the second concept is the concept of time. Now, nothing is more fundamental to our experience of the world than the temporality of that experience. We experience things in time. Now, what is the exact nature of our intimate experience of time? Now, is that a problem of language, philosophy, psychology, neuroscience, physics, or all of these? Now, such questions have been debated ever since we have records of people thinking about the nature of things. People have thought about the nature of time. And I'm not going to try to delve into that enormous subject. But what I want to do instead is appeal to something which could stand for our intimate experience of time, and that to take the place of our intimate experience of time, and that is children's experience of time, or at least what we know about children's experience of time, to stand for something which is more intimate, more innate, less learned than what we would say about time. So I went to a conference about time in which there were physicists and philosophers, neuroscientists, and a psychologist, an experimental psychologist called Teresa McCormack, who works at Queen's University Belfast. And from her, I learnt these aspects of children's understanding of time. Now, any mistakes that I made here are entirely mine and not Teresa's, but this is what I learnt from her. Young children know that events have an order. They know that first it's bath time, then I brush my teeth, and then I go to bed. So they can order events in that way. They also learn, and they learn quite young, that events can be grouped into past events which are already completed, present events which are ongoing, and future events which are yet to occur. And they also learn about clocks and calendars, but they do that much later, and they find it difficult. So it's hard for children to learn about clocks and calendars. But they find the notions of ordering of events and the notions of past, present, and future easier to learn. Now, why do they find clock time and calendars more difficult? Why is that something of a struggle for them? Well, my claim is that that's because it requires a conceptual picture of things that are happening right now but are far away. So if you think about it, the notion of the date must mean that there's such a thing as today, the 5th of October this year, everywhere. The notion of the time, which is what your clocks and watches are measuring, requires a notion of a global moment of now. And that's something which children don't have in their day-to-day, everyday experiences. They just experience things locally to them. But in order to have this concept of time, as measured by clocks and calendars, you need to conceptualize the idea that there is such a thing as right now in Japan, and right now on the moon, and right now on Jupiter, and right now in Alpha Centauri. And Newtonian space-time accords with that idea that there is such a thing as a global moment of now, that time ticks away at the same rate for everyone and everything, no matter what it is, so that you can stack up space at this moment right now, and later on space at the later time, and space at a later time. These three-dimensional slices of space can be stacked up, one on top of the other, into a full four-dimensional space-time. And that's the Newtonian picture of space and time. Space-time in general relativity is also four-dimensional, and in this four-dimensional space-time of general relativity, which, remember, is curved, which is what I've tried to draw here on the picture, there are events, such as an event of my birth, which I've drawn here. I trace out a world line in space-time as time passes for me. And finally, there's the event of my death. So that's my world line in space-time. And everything and everyone traces out their world lines in space-time. There's the world line of photon that's created at some supernova and is witnessed by me at a particular event on my world line. Here's someone else's world line and an event where we meet. And everything and everyone traces out their world line in the four-dimensional space-time of general relativity. And there is no such thing as a global moment of now. I drew in those slices just to guide your eyes, but in general relativity, there's no global moment of now. It doesn't exist. There's no way to there's no physical notion of simultaneous events simultaneous to me here, stretching across the whole universe. Such a thing doesn't exist. There is just space-time and world lines in it. So there's no global time in general relativity, no concept of a global moment of now. So this modern scientific view of time in GR accords better with our childlike inner space temporal concepts of the ordering of events local to us. Because a world line in space-time is ordered. The events on my world line are ordered. My birth comes before my death. But there's no way in general relativity to coordinate the events local to me with events globally in the universe. So general relativity, the picture of space-time, accords better with our intimate experience than the space-time of Newtonian physics. However, our inner space speaks to us of a dynamic passage of time, whereas the picture of the world that general relativity gives us is of a whole four-dimensional block. You see here I've got my birth and my death drawn on this picture of space-time. If that block picture of the world is right, then the events of the future are just as real as the events of the past, and they just all exist in this block in a timeless way. So there's some kind of tension here between our experience of the passage of time and the block universe picture that general relativity offers to us. Can this tension be relieved? And here I'm going to move into a more speculative area of physics that is under investigation by myself and my colleagues. A theory of space-time that I'm actively working on with my colleagues is that space-time only appears smooth and continuous to us at large scales, and that at small scales it's fundamentally atomic or granular. These scales are very, very small, so small that there are 10 to the 240 of these space-time grains or space-time atoms in the observable universe. And the proposal made by my colleague Raphael Sorkin of the Perimeter Institute in Canada, is that the passage of time that we experience could be the coming into being or the birth of new atoms of space-time. Now, this is a speculative proposal. We don't know whether space-time is granular. So far, we haven't tested this theory properly. So we need to look at data and test our predictions in order to find out whether this is really the case. So inner space and outer space, in this sense, become intertwined. Our inner space speaks to us of this dynamical passage of time, but we need the phenomena of outer space in order to test such a theory. Both inner and outer space are necessary to our understanding of the universe. So let me end with this thought. Abdus Salam, who is the founder of the theoretical physics group at Imperial College where I work, said that scientific thought and its creation is the common and shared heritage of humankind. General relativity and the understanding of the world that it offers belong to everyone, and in this year of the 100th birthday of general relativity, you have come here to claim your inheritance. And I'll end there. Thank you.